Hi everyone, this is our Introduction to Local Geology lecture. This lecture is meant to complement what you've read in your textbook about soils and also to help you make sense of some of what we will see in the field on our local field trips. The specific learning goals are to develop an understanding of the origin of some of our local topographic features and abundant rock types, and also to develop an understanding of the properties of some of our local soils, including selected soils of the Cascade and the Klamath Mountain regions. Let's begin by recalling some of what you already know about soil. Soil is essential to plant growth. This is where plants are taking up the nutrients and also the water that they require in order to survive. Recall also that soil development is a dynamic process and it's dependent upon 5 interrelated factors, including the kinds of parent material that are in a particular area, the local climate, the topographic features, biological factors including the plant community, animal community, and the community of microorganisms, and also the amount of time that the soil has had to develop. In this lecture, we're primarily going to be looking at parent material and topography in the role that they play in soil development. We're going to start by examining the structure of our planet, starting with the center or the core of the Earth, which we see here in silver. The core of the Earth is extremely hot, and it also is made up of elements that are relatively dense, more dense than the elements in the mantle and the crust. Moving out from the core, we see the mantle. So the mantle is shown here in yellow, orange, and red. And the mantle is made up of rocks of intermediate density, including rock that is rich in elements such as iron and magnesium. Moving out from the mantle, we have the crust, which is kind of like the skull bones of our planet. The crust includes rocks that are the least dense, silica-rich rocks, and it makes up the outer part of our planet. It includes both oceanic and continental crusts. So the oceanic crust is the bottom of our oceans, and then the continental crust makes up our continents. The crust is broken up into plates, and those plates are floating on the mantle. The movement of those plates is driven by convection. So if you take a look at the diagram at the bottom of your screen, you can see a red arrow moving out from the core of the Earth. That red arrow is showing the direction of the movement of the matter in the mantle. So I mentioned that the core of the Earth is really hot. The warm magma is going to rise, and then when it hits the crust, it's going to move to the right or to the left. So you see those blue arrows moving in opposite directions. Where this is occurring on the planet, we would have plates, tectonic plates of the crust moving away from each other. And there are 3 options for how tectonic plates can move relative to each other. And the first is the one that we just looked at on the previous slide. They can move away from each other. And these are called divergent plate boundaries. So we see here in the diagram at the top of this slide on the right, we have 2 plates that are moving away from each other. And as those plates move away, magma is going to fill in the gap between the two plates. Divergent boundaries are characterized by rift valleys and oceanic ridges, like the Mid-Atlantic Ridge in the Atlantic Ocean. That ridge is pictured below in the area in Iceland where it rises above sea level. Divergent boundaries are also associated with the formation of volcanic islands as magma rises to the surface, and also with earthquakes, which I'll explain when we look at the diagram on the next slide. So let's start by taking a look at the diagrams in the circles on these slide and on the slide, and let's start by looking at the one on the top. So you can see this is an area, this is showing an area where we have two plates diverging. They're moving away from each other, and we can see that from the blue arrows. But it's not like the line in between these two plates is completely straight. It's jagged. And so that means that some of these areas in red, we're going to have what's called a transform boundary, where plates are slipping past each other. And this is where we get earthquakes. So that's why those divergent boundaries that we just looked at are also associated with earthquakes. It's because of the many transform boundaries that form as plates move away from each other, as we see in this picture. The third option for how tectonic plates can move relative to each other is that they can be moving towards each other. This is called a convergent boundary, where plates collide. And in the diagram, we can see we've got a continental plate converging with an oceanic plate. Oceanic plates are more dense than continental plates, and so we can see that this oceanic plate in this collision is actually going underneath the continental plate. This is called subduction, when one plate slides underneath another. And this type of convergent boundary is associated with a deep sea trench. You can see off the shore of this continent in the diagram, you can see we have an area of deep water where the subduction is occurring. It's also often associated with the overriding edge of the continental plate getting crumpled and uplifted. There's often accretion occurring on the continental plate, so formations that are on the subducting plate can get tossed up onto the continental plate as the oceanic plate is subducted. And these convergent boundaries are also often associated with volcanism, and you can see in this diagram inland from the area where the subduction is occurring, we have magma forming and then rising to the surface. The movement of the tectonic plates and other geologic processes form the rocks that make up the parent material of soils. Geologists recognize three main types of rocks, including igneous rocks, and igneous comes from the root ignite. Igneous rocks are formed from cooling and solidification of molten rock. There are two main types of igneous rock. The first are called intrusive or plutonic igneous rocks, and these are rocks that formed from magma that cooled slowly inside of the earth. They're characterized by large crystals that you can see in the image, and the upper image on the screen. That's granite. So you can see those large light and dark crystals. Those occur because this rock formed slowly inside the earth. The other type of igneous rock are extrusive or volcanics. And these are rocks that form from extruded molten lava. So the magma comes out and it cools really quickly, and you end up with rocks like basalt, which is pictured here on the bottom, that have much smaller mineral crystals in their structure. Sedimentary rock is another rock type. This is the most common type of rock that we have on the planet. So 75% of the Earth's surface includes sedimentary rock. Sedimentary rocks form from consolidation of particles from another source, or from another rock. So it could be weathered igneous rocks, or weathered metamorphic rocks, or weathered sedimentary rocks, other sedimentary rocks. So particles are deposited by wind, or they're deposited by water. They become consolidated as more weight builds up on top of them, and then eventually the particles become cemented together as the minerals dissolve in water and then recrystallize. We can identify different types of sedimentary rocks based on the size of the original particles. So the rock pictured in the upper picture on this slide is shale, which forms from really fine particles, and then the rock on the bottom is sandstone, which forms from more coarse particles. The last type of rock is metamorphic rock. And these are rocks that are altered from their original state, either igneous or sedimentary rocks that are altered by heat and pressure. The example that we have here in the photograph is gneiss, and we can see these sort of wavy lines. That's a common characteristic of metamorphic rocks. So these rocks, these sedimentary or igneous rocks, become plastic and they move because they're exposed to a high amount of heat and a high degree of pressure. Some characteristics of the original parent material remain in the metamorphic rocks, but they are altered by heat and pressure. Now let's take a look at how some of these geological processes have played out locally to shape our terrain, and we'll also take a look at some of the locally abundant rock types. We have a very diverse geology locally, including the southern portion of the Cascade Range, which is outlined on this map in blue, and the Klamath Mountains to the west, which are outlined on this map in pink. Each of these has a unique origin, but both have been heavily influenced by subduction. So the volcanic activity, we'll start by examining the Cascade Range. The volcanic activity in this area has been caused by the subduction of the Gorda Plate, which we can see down here in the southern region of this map, moving eastward underneath the North American Plate. If we take a look at this map, we can see that there is a large amount of volcanic rock in the Cascade Range, which is no surprise given the amount of volcanism that's been occurring here as a result of that subduction. Some of this volcanic rock is part of the Western Cascade series. It's older in age, about 35 million to 17 million years old. There are also more recent or younger rocks, which are part of the High Cascade series, and those rocks are about 400 million years old or more recent. So the High Cascade series includes the activity that's formed Mount Shasta and also Mount Lawson. This volcanic activity has produced a variety of fine-grained igneous rocks. The picture on the top here is of basalt, which is an extrusive extrusive igneous rock that's dark in color. It has a lot more iron and magnesium in it, which gives it that dark color. On the bottom, we see a picture of rhyolite, which is another extrusive igneous rock. It's lower in magnesium and iron and higher in silica, which gives it its lighter color. Andesite, which we see a lot of on Mount Shasta, is intermediate in its chemistry and color. The recent volcanic activity has had a profound effect on our landscape within the Cascades Range. Here we see a picture of Mount Shasta, which dominates our local landscape. Mount Shasta rises 10,000 feet over the Shasta Valley to over 14,000 feet. It is a stratovolcano, which means it's formed from successive volcanic eruptions, and it has alternating layers of volcanic ash and lava. It has formed from repeated eruptions over the last 300,000 years. Its impact on our landscape extends really far within our region. If you take a look at the map on the bottom, you see this circle showing the area of Mount Shasta, representing the area of Mount Shasta in the bottom of the map. And then you see this beige region moving northward. This represents debris from one of the largest debris avalanches geologists have ever measured. So there's a huge amount of debris from Mount Shasta covering the Shasta Valley. This debris traveled as far as 49 kilometers, and it covers 675 square kilometers of the Shasta Valley. So we've got this obvious volcanic feature, Mount Shasta, but then we also have lava flows, volcanic debris, volcanic ash throughout the region. The recent volcanic activity has also had a really big impact on our local soils. We have a huge variety of parent materials, including volcanic rock, volcanic ash, mud flows, glacial till at higher elevations where we have glaciers on Mount Shasta. We also, as a result of the diverse terrain, we have a variety of climates. We'll talk more about climate next week. And we also have a variety of topographic features and slopes. So I tried to come up with, given all of this diversity in parent material and climate and terrain, I tried to come up with some generalizations about the soils within the Cascade Range locally. We generally find that soils are deeper at lower elevations. So as sediment moves off of steep slopes downhill, we find more deposition occurring at lower elevation and therefore deeper soils. We find that soil organic carbon is higher at higher elevations. This likely relates to the climate. So at higher elevations within the Cascade Range, it's going to be colder. Decomposition rates are going to be very slow, and that's going to cause the organic carbon to build up within the soil. We also find in general that pH is lower at higher elevations, so we have more acidic soils at higher elevations. This is likely due to increased moisture at higher elevations, and we'll talk more about why we see more precipitation occurring at higher elevations next week. But as we get more rain falling down or snow melting, that's going to leach nutrients out of the soil, and it's going to leave behind protons, which contribute to higher acidity and lower pH. In general, the soils of the Cascade region are known to be productive, and that means they tend to support plant growth. So they provide the nutrients and water that plants require. So they're really porous soils that tend to hold water in a way that plants can take it up. Now let's take a closer look at the Klamath Mountains, which are located to the west of the Cascade Range. The Klamath Mountains include subranges like the Siskiyous, which are located north of the Klamath River along the border between California and Oregon, and also the Trinity Mountains, which are located north of Redding and include features like Castle Crags and Mount Eddy. The Klamath Mountain geology includes a composite of accreted terrains. These terrains accreted on the continent as subduction was occurring. As a result, these terrains become younger as you move westward. So Mount Eddy, which is on the eastern end of the range, has the oldest and tallest rocks. To try to understand this a little better, I found a quote by Ellen Morris Bishop, and she referred to the accretion of these terrains in the Klamath Mountains as a collage of exotic geology swept onto the prow of a westward moving continent, like pond scum on the bow of a giant canoe. So as subduction was occurring under the North American plate, more and more rocks and material were getting flung up onto the edge of the continent. So the most recent rocks would be further westward. The older rocks, which were deposited on the continent longer ago, would be further eastward. This origin explains the diversity of rock types present. If you take a look at the Klamath Mountain region on this map, you see there's a huge variety of rocks, including metamorphosized sedimentary rocks, metamorphosized volcanic rocks, igneous intrusions like we see in the Castle Crags, and also ultramafic rocks. Let's take a closer look at those ultramafic rocks and the soils that they create. So the Klamath Mountains include the largest outcroppings of ultramafic rocks in the world. And this is notable because these rocks are really unique. So a lot of people refer to these rocks as basement rocks because they form relatively deep within the crust of the earth. And these include rocks called peridotite and serpentine. These are two kinds of ultramafic rocks. They both have similar mineral compositions. They're both really low in potassium and calcium. Recall that these are both nutrients that plants require, and they're both high in magnesium and iron. And these are essential nutrients for plants as well. But in the case of magnesium, if it's present in the soils in really high concentrations, it can have a negative impact on the plant's ability to take up other nutrients such as calcium. These basement rocks are also sometimes high in metals such as nickel and cobalt, which can be toxic to plants. So as a result, these rocks generate soils that are uniquely challenging to plants, because in some cases they're lacking the nutrients that plants require, and in some cases the metals are so high that they're toxic to plants. Let's take a closer look at these two basement rocks, peridotite and serpentine. So peridotite is an igneous rock. It generates soils that are red in color. It's really rich in iron, so when that iron oxidizes, the rock becomes red. It tends to stick together in larger fragments, so it generates really rocky soils. And because it sticks together and resists breaking down, we tend to see peridotite on steeper slopes compared to serpentine. Serpentine rocks are pretty brittle. They break easily. They don't hold up on steep slopes, so they're often associated with landslides on steep slopes. And serpentine is a metamorphosized form of peridotite, which explains why they're so similar in their mineral composition. So serpentinization occurs when peridotite is exposed to water during subduction. So it causes the rock to change. The serpentine rock looks totally different. It's gray or green and waxy. These rocks are really brittle. As I said, they split easily, so you generally won't find serpentine on really steep slopes. It's often associated with landslides on really steep slopes. Not all of the soils in the Klamath Mountains are as challenging for plants to grow on. Recall that there's other parent material, including metasedimentary, metavolcanic rock, and also granite. So the chemistry of the soils derived from these rocks is much more typical and conducive to plant growth. It's hard, once again, to look for generalities in the soils of the Klamath Mountains because there's so much diversity in the terrain and also in the climate. There's a steep precipitation gradient ranging from 500 millimeters of precipitation per year to 2,800 millimeters of precipitation per year on the coast. This is going to drive the pH and the soil moisture as it did in the Cascades. We're going to see pH decline with elevation, soil moisture increase with elevation. Once again, we see higher soil carbon at higher elevations where decomposition is slow. And we'll also see soil development being slow on steep slopes and at high elevations. In conclusion, you should understand what subduction is and how it has influenced the volcanic terrain of the Cascade regions and the Klamath Mountains. And you should understand how the local parent material, so the rock types, and also the local landscape features affect the soil formation and the soils. If you're looking for further reading on these topics, I recommend the following sources which I cited in this presentation.